Now, about geometry. So there is just a few facts in geometry that I just want to dump on you because it will make the class so much better. And something that I should have shown you is about tangent lines. You know, Calculus 1 has two obsessions, and one of them is tangent lines. You can draw tangent lines to all kinds of things, not just circles. But tangent, if you look at it as intersecting a line and a circle, there are obviously three possibilities if they are in the same plane. And if you solve a quadratic system of equations, it will boil down to a quadratic equation where how many solutions does a quadratic equation have? Well, 2 or 1 or none. If you had looked at the nonlinear systems, you've seen something like that. This is what we call a tangent line. The nice thing about tangent lines is there is not that many facts. There are just two facts. So by elimination, when you see a tangent line, there is not that many options. There are just two very important theorems about that. Number one is that if you have a tangent line, then there's just one intersection point with a circle. That point has a fancy aristocratic name. It's called the point of tangency. Surprise, surprise. And then the big deal is that there is a right angle here. I have seen this wrong picture just way too much, where people put the right angle here. Don't do that. So one way to avoid that is, well, one way is to suffer because of that error. Another way is try to store this fact in language. The theorem goes like this. The language is the radius drawn to the point of tangency and the tangent line are perpendicular. And then you will, if you store this fact in language, you're not going to be able to put the right angle at the wrong spot. The second fact is it's kind of it puzzles me because it's a fact that's just so obvious in isolation, but when it pops up inside a geometry problem as the thing that gives you the solution, it's always, to me, like a little surprise party. And that is, it's kind of a weird one. If you have, you know, this trinity, if you have a point and a circle, how many tangent lines are from the point? Well, if your point is on the circle, there's just one tangent line. If the point is inside the circle, there is no tangent line. And if the point is an external point, there are two tangent lines drawn to the circle. So again, that 2 or 1 or none sort of a deal. So let me just say that this whole thing is symmetrical. This line, the one that, this is the external point from which we drew two tangent lines. By the way, these two tangent lines and the angle between them in architecture, that's what we call the angle of view. So in what angle do you observe that object? So it has practical applications, but this whole thing is symmetrical. So these two angles are the same, these two angles are the same, but the theorem only states that these two line segments are equally long. And this is it. These are the two facts about tangent line. There is nothing else. So whenever there is a circle and a tangent line, I draw in with that line because there is not that much else. If PB and PA are tangent to the circle. Now, if you looked at the handout about similar triangles, you have already seen that because I'll show you why. Are tangent to the circle, then the length of PB equals to the length of PA. More is true, but for some reason, this is the theorem with the big fuss. And if you have seen the in detail the similar triangles handout, you have seen two circles with their common tangent lines. And then if you connect the two centers, that will intersect. That will also contain this point. And so you see, because of this right angle, because it's a common tangent line, these two lines are parallel because they're perpendicular to the same tangent line. And then there is a very obvious pair of similar triangles. You see this little one and then this big one. You might have seen that if you looked at the similar triangles and that. Now, before we move on, there is one more thing I want to show you, and that is what happens when two circles are tangents to each other. And again, there is a convenient scarcity of, there is not that much to think of. There is just one theorem about it. And it's literally just one. So if circles are tangents to each other, then the line connecting the center of the circles also contains the point of tangency. But what is cute is that there are two ways two circles can be tangent. There is internally and externally. The externally, I think it's pretty intuitive that that happens. So if you take the two centers and you connect them, that line will contain the point of tangency. But it's less intuitive, but still just as true, is if this is a internally tangent. So when you connect these two, you just have to keep going and then you will hit that. That's the point of tangency. And if you're given three numbers, the radius of the small circle, the radius of the bigger circle, and the distance between the centers, that will pretty much tell you what's going on here. If you add the two radii, you have to get the distance between the centers. That's when you get this case. Think about what will give you that case. And that's it. There is a delightful scarcity of facts. So if circles are tangents to each other, and I actually wanted to show you a problem like that. There's no other option than connect the centers and the point of tangency is on that line. There's nothing else under the sun, which is kind of good. Okay, so these are the facts that you need to know about tangent lines. I wanted to show you an example about the Pythagorean theorem. Well, it's not that you have a right triangle where two sides are given and you have to find a third side. Most Pythagorean theorem applications don't even have a straight line in them. And so, for example, imagine that, well, we're just going to make it up then. Imagine that you have two circles equally. We can rephrase the whole thing in 3 dimensions. You have two spheres like pool marbles or pool balls that are sitting in the ground and they're touching each other. And let's say that the bigger the radiuses of these two are both 6 units. And there is this third one that is touching both circles and the ground. And that radius is what we have to find. This sort of problems, I think almost without exception, boil down to the Pythagorean theorem, surprisingly. So I just wanted to show you how that one goes, especially now that we talked about tangents, right? Because I might have to draw a bigger picture. There is a lot of very cute things. So first of all, we can think of this as 3 circles and a line, and everybody's tangent with everybody else, right? The line is tangent to all 3 circles. This circle is tangent to the other 3 guys. Yeah, everybody with everyone tangent. Or you can think in terms of 3 spheres and the floor. It's the same problem. So if someone gives you the problem in 3 dimensions, this is the picture you draw, and you solve the 2-dimensional problem. So let's see. Let's use the line. So if we want to exploit the fact that there are tangents, the one thing we can do is draw in the perpendicular line the radius from the center to the point of tangency. So circle 1, the line is tangent to circle 1, boom. That's the only way to use it. The line is tangent to circle number 2, boom. And how long are these line segments both?
They're both 6.
6, exactly. And then this cute little one, this here is little r or x, if you want to label it. I think I'm going to go with r, x long. So we have it's like a word problem, but now we used all the facts about the line. These are perpendicular lines, and these are 6 long, and this is this little r long. Now, what's left is, well, the circles tangents to each other. So the two big circles at tangents to each other means connect the centers, and that will contain the point of tangents. Do we know how long this line segment is?
Wouldn't that be 12?
Yes, it would. Excellent. I'm not sure what labels to write there yet. And then the only thing we haven't used that is the little circle is tangent with everybody. Well, with the other circles. So this is without thinking. Just this is how we sort of not even exploit, just translate the fact of tangents. And then, you know, oftentimes a geometry problem, if you were struggling over it, which is what you were supposed to do, is basically the whole thing comes together if you just draw in one magical line. But that magical line might take 10 drawings, hours of thinking. Instead of computing in geometry, we draw a picture and we try to draw things until we stumble into the magical line. Now, the magical line in this one is this. And we're going to write the Pythagorean theorem on this triangle. Now, do I have to zoom in? I might have to zoom in. And there is a lot of things that I find lovely about this problem. How long is this vertical side? And you can tell me in terms of a number, but in terms of a number and r, little r, you might. How long is this line segment? Okay, let me ask you this. How long is this?
That would be 6, right?
That would be 6. How long is this?
2.
No, it's little r or x. So, and you'll get used to it. These are the kind of things. It's what geometry is in geometry, what word problems are in algebra. This is 6 minus r. You see it now? This is 6 minus r. This cute little thing is r, and this whole thing is 6. Now what about the hypotenuse? How long is this? That might be easier. Remember, we connected the center of two circles.
6 plus r.
Yes, it's 6 plus r. That's the hypotenuse. That's opposite the. And this side.
Would it be 6? Would it be r plus 6 minus r? Or
Yeah, it would be 6. Exactly. I don't know how you got it, but it's there is a lot of right angles. And this here is, so it's basically 6. This is the same. This is a rectangle that I'm outlining. Why do we know that? This is vertical because it's perpendicular to this is so because of the symmetry, because these two, this is a much harder problem. If one of the spheres or one of the circles is smaller, then it's kind of a beast. But right now this is just 6 there. Do you see it? And then there's the Pythagorean theorem says that 6 squared plus 6 minus r squared equals 6 plus r squared. I find this lovely that the difference and the sum both appear. Oops, I need to zoom out. And then the equation is not even quadratic anymore. R squared will cancel out. So we can just say 36 plus 36 minus 12r plus r squared equals to 36 plus 12r plus r squared. R squared is dead. 36 is dead. There is another 36 here, and we can add the 12r to the other side. Look how cute and simple it got. R is, I guess, 3/2. We can cancel out 12. So it's 1.5. And then look back. You know, we should always have a reasonable picture and then ask, does this sound reasonable? This is 1/4 of 6. So it's not beyond the realm of possibilities. I believe that's the correct answer. But just to show you that a lot of the Pythagorean theorem applications are coming from curvy things, touching each other. They all boil down to Pythagorean theorem. Any questions about this one?